So, good evening, everyone, and welcome you again for the webinar series by IIT Alumni Center, Bangalore. And as most of you know that the center is a unique networking platform and aims to establish collaboration between academia and industries. So, means people can bring the projects, relevant projects related to any subjects, and we really look forward to establish these collaborations and facilitate these collaborations so that research component or industrial components can be taken forward. So our previous webinars, our speakers were talking about bridging the gap between innovation to implementation in healthcare. And today, again, along the same line, we have the talk on artificial intelligence in drug discovery. So pretty interesting webinar today. So our speaker is Professor Arvind Rao from Department of Computational Medicine and Bioinformatics, Biostatistics and Radiation Oncology at the University of Michigan. And his group uses image analysis and machine learning methods to link image-derived phenotypes with genetic data across biological scales from single-cell tissues to radiology data. And these methods basically find application in radiogenomics and drug repurposing based on phenotypes screen and spatial profiling in tissues. So brief background about Dr. Rao is Arvind received his PhD in electrical engineering and bioinformatics from University of Michigan, and his specialization in transcriptional genomics. And he was also the postdoctoral fellow at Carnegie Mellon University. And there also his specialization was in bioimage informatics. He is a fellow of American Medical Informatics Association, AMIA, and he is a Royal College of Pathology in UK, is a member of that, and also American Association for Advancement in Science. So, and this talk is going to be moderated by Dr. Vasan Sambadamurthy. He's a senior vice president at Budwork Research Inc., and which is a clinical stage biopharmaceutical company developing a novel class of broad spectrum of antibacterial agents and also to treat patients with critical care. So Dr. Vasan has 20 plus years of professional experience in vaccine discovery and drug development. And he has been associated with major global corporations like Novartis, AstraZeneca, and Biocon. And Dr. Vasan is also recipient of several awards. So no wonder. And he has also published a lot of publications, patent, and mainly focusing on this, the immunology and medicine. So today's webinar will be co-hosted by myself and Dr. Sushila Venkatraman. And for audience, you please post your questions in the Q&A box, and this will be taken up during the discussion and the short break. So please do so. So over to Dr. Rao.
So what I thought was I would, and I apologize again, I was just mentioning to the organizers that I have a unique situation today. I have to basically decide between having an internet connection and having my camera on. Turns out the internet connection one wins. So I unfortunately will not be able to go on camera, but if things improve with internet, I can probably try at a later time. So with that apology out of the way, I just wanted to say that I'll talk a little bit about AI in the drug discovery pipeline, using it for various aspects of target discovery as well as for molecular modeling. But the hope is to very quickly pivot to what's happening even more recently. As you all know, the past year has been really exciting from the perspective of AI in science, with the Nobel Prizes going to AI, those kinds of things. So it really perhaps is a good time to discuss what does that mean for all of us as a community going forward. And so I just wanted to spend some time discussing that part as well. So as you all know, last year we had 2 Nobel Prizes in science, one in physics, one in chemistry. The one in physics went to Hopfield and Hinton, both for work around neural networks. And while I'm not sure if either Hopfield or Hinton had a physics undergraduate degree, I don't think they are physicists by any stretch of imagination. They are both, heavily into computer science. And then in chemistry, the same way, we had David Baker, Dennis Hassabis, and John Jumper. These two gentlemen work for DeepMind. David Baker works for University of Washington in Seattle, and he's probably the closest to being a chemist as an academic, but these two are again computer scientists, right? So it's a very interesting time because now the pinnacle of academic achievement in some sense, the Nobel Prize itself, has been taken by AI and by folks who are not necessarily card-carrying specialists in that domain. So what does that mean? And so, based on this very picture, there has also been a more recent challenge. It's called the Nobel Turing Challenge. And it brings two very important historical figures together, two scientific figures together, Alfred Nobel, who obviously is a name behind Nobel Prizes, and Alan Turing, the person behind modern computer science. And so the Nobel Turing Challenge is a very interesting challenge. It says that by 2030, which is not too far from now, a completely AI-based engine will make a Nobel Prize winning discovery. That's the hypothesis, right? And so just to put it in perspective, how far is 2030? It's not that far away. And to make it even more direct, it basically means that next year, we are right now in July, August, that's when all the new kids are going to college. So the students that start next year in August, that student pool, when they graduate in 2030, this will be a reality, right? So what are we preparing these students for in such a world where you don't even need a human to be involved in doing scientific activity, right? So I wanted to be able to spend some time on that, but we'll revisit this in some time. And this obviously prompts a lot of interesting downstream conversations. Last year was the year of AI in science. This year is the year of multi-agentic research workflows, which means why stop at just one AI model, right? You can basically now connect multiple AI models in some kind of workflow and apparently do even bigger things, right? So this lays out a very interesting realm of possibility for us, but also brings questions about what would AI transparency, AI regulation, AI ethics look like? What would the interplay between humans and AI look like? What would human AI hybrids, if I could use that phrase, what would that look like? And while you might have heard this statement now way too many times on LinkedIn or elsewhere is, AI won't replace humans, but humans that use AI will replace humans that do not use AI. That's the typical statement that's made these days. But for a human to be able to fruitfully use AI, there needs to be this concept of human AI collaboration, which also brings into aspects: what does it take to do science at the highest level, reproducibility, reliability, robustness, calibration, uncertainty, quantification. All these aspects have to now start entering our collective consciousness. So let me start with, just a brief, case description of one case where we used AI for drug discovery. And really the principle of this comes from a concept called phenotype-guided drug discovery, where essentially what you're trying to do is you have a high-throughput robotic pipeline wherein you can take these. So what you're seeing on, let me try to get you a slightly different pointer. Okay, so what you're seeing here is a glass slide, but instead of just being, one area of measurement, it actually has 96 areas of measurement. It has 96 wells etched on this glass slide or this glass dish. And what you can now do is you can do experiments in high throughput format, which means you can now take these 96 wells that have been etched into a glass plate, and each well becomes its own petri dish, right? And what does that let you do? It lets you do experiments at a very high throughput. What kind of experiments? One kind of experiment you could do is you could pipette cells into multiple different wells and then add drugs of different kinds to ask how well does the drug arrest the disease state in these wells, right? So following that kind of logic, this is an experiment where my colleagues, in fact, they were trying to look at a disease called triple negative breast cancer. Now, this is one of the worst kinds of breast cancer in the sense it has got some very poor prognosis. I'll say a little bit more about it later. But it's triple negative for people that are enthusiastic to understand why the word triple negative comes along. It's because it's negative for the HER2 receptor, the PR receptor, right? And the progesterone receptor. So what happens is that ER, PR, and HER2, estrogen receptor, are all absent in this particular cell. And so endocrine therapy, hormonal therapy will not be able to help these patients. But it affects a very, very big swath of patients, both in Southeast Asia and in Africa. And so it's really, really difficult to treat this disease, even with aggressive methods like surgery, because things remain, they can metastasize so on. So my clinical colleague by name Naoto Ueno, who I worked with when I was at MD Anderson Cancer Center, had the following question. He said, can we do something using high throughput, high content screening that can help us prioritize drugs that are capable of changing the state of disease from this level of unfavorability to something a little bit more favorable? So what does that mean? I'm an engineer. I'm not a doctor by any stretch of imagination. So I said, yeah, help me understand this a little bit more intuitively. So he said, let's take this example. This thing on the right, a palm with open stretched fingers, is what we call the mesenchymal type of cell, which means that these are cells that have finger-like protrusions on them. And these protrusions actually help the cells to move. On the other hand, we are looking to alter the state of these morphologies of these cells to a situation like on the left-hand side, where we want to be able to make it retract its projections so that they're not as mobile as before. The goal being that if you can actually arrest the mobility of these cells, they become much less aggressive. They don't get away too far. So when you radiate these patients or give them some kinds of targeted treatments, the chance of getting all these cells now becomes much, much higher. So in principle, the goal is to be able to alter a cell's morphology, which hitherto used to be like this, and change it to something that looks like this. All right. So that's the intuition. Let's look at what that means in terms of real data. So what we now have, like I told you, we have these 96 wells. And for each well, you have some positive, on each plate, you have positive, negative controls, which is supposed to tell you what should happen and what should not happen. And that helps you calibrate your assay. But then on the remaining wells, which are colored here in blue, you actually can have a robotic handler go in and pipette different amounts of drugs into these different wells, and then ask the question, if I took pictures of these different wells with a high content microscope, I get images. Can I use these images to quickly triage which cells are undergoing a favorable change in morphology versus are not changing at all? Right? That's really the idea. And so the goal is we have tons of images coming through this high throughput microscope at unprecedented velocity in the order of 20,000 to 30,000 images, and how we need to do some kind of computer vision kind of algorithm to be able to flag those wells where we have the change in phenotype or appearance from this to this. Okay? And to give you a sense of real data, because this picture is very nice as intuition, but in reality, the data looks pretty messy. So here's an example of the open palm and the closed fist on the left and the right. So you can see you've got to really stare at the screen. You kind of have to look for what you're talking about. And then eventually you can convince yourself that on average, the number of cells that have these projections is much longer in this, is much more prevalent in this right-hand side image compared to this left-hand side image. So when Naoto asked me to build a algorithm, the first thing I asked him very, very, I guess, naively was, hey, give me training data, which means give me examples of what these two kinds of categories look like, and I can build you an algorithm. So he spent a whole afternoon looking through these images very, very carefully, and he came up with 33 examples. Now, if you're living in the machine learning or deep learning world, 33 is not a great number to learn from. But I felt guilty because, I'm asking an oncologist who should be treating patients to instead spend his time in my lab looking at images. And so I felt very guilty about using resources untenably. So I said, let's see what we can do with 33. What's the best that we can do? And so the idea is to build a model let's just call it model being a little bit abstract, that lets you distinguish these two kinds of images. Now, when we did this initially, this was a bit of an engineering exercise. But now, I don't have to convince you too hard that classifying images of different kinds is not very hard anymore. Right? You have very good computer vision algorithms, sometimes even implemented at the level of, very, very easy to use routines that you can use to discriminate category A from category B. And here the morphological changes are pretty stark. So it's not like something subtle. It's pretty stark. And so building a model to do this is not hard. So intuitively, I'm just going to show you we were able to do this. And the pipeline looks a little bit like this, right? You have to clean up the data, you do some pre-processing of the data, remove the noise, try to extract some features, do some data mining, and then try to see if it maps to something biological. So I'm going to skip this in interest of time because I know we have got a type of schedule to keep. So just to believe me when I tell you that we had to clean up this data, the obvious raw data from the microscope is not great. To give you an example, I don't know how much you can see this, but if you look very closely at these images, you can probably see lines that go diagonally from left to right. They're going downwards. And just to tell you where that's coming from, that's basically a scattering artifact that's induced by the kind of plates that we are working with. Because there's a lot of out of focus problems with the microscope. These are, when you're doing microscopy in high throughput, these problems are very, very, routine. So one has to be able to clean up that. So in some sense, we all agree that data mining, data processing, pre-processing is perhaps the unspoken hero, right? It's like nobody talks about it much, but probably it's about 90% of the work, right? Because once you clean up the data, then you know what to do. So I'm skipping all in the interest of time, but I'll just tell you that we extracted a whole bunch of features, built an algorithm, and it was a version of the random forest algorithm, which is a very old and popular machine learning algorithm. But let's see where it lands, right? So where it lands is once you build this model and you run this on all the images that have been seen so far, based on the 33 examples, you find about 351 genes which when altered will convert this change in phenotype or appearance from the finger-like protrusions to this closed fist-like appearance. So that's basically 351 good leads, quote unquote leads. Now, if you speak to anybody in pharma and say you have 351 possible hits to follow up, they'll probably be less impressed because each lead is a whole trial. And unless you have some methodological and systematic way to filter which ones don't work, you can't run 351 clinical trials. That's not going to work. Each clinical trial is at least, at last count about $2 billion. So this just does not scale, right? So you need to find a way to keep reducing this number of genes. How do we do that? So the obvious perspective would be to go back to my human expert, Naoto in this case, and say, hey, remember you only gave me 33 examples. Can you give me more? At which point Naoto asked me, well, how many more? At what point will you be satisfied that the training set is good enough to be able to do a better job? At this point, we were at a fork and we said, well, can we learn from other engines? And at the time, I'm sure many of us in this group have used at least one of these interfaces at some point, right? You all used a version of Netflix or Amazon Prime. You all used some version of Amazon.com for shopping, be it Blinkit, be it Zepto. You use some version, or you use some version for music streaming, etc., etc. And almost always, the underlying theme is a concept called collaboration filtering or recommendation engines. And how do these work? They work in the following way. The day I start my Netflix account, it gives me 10 random movies to watch. Depending on which one I pick or which one I watch to the end, or which one I actually watch to the end and give a good rating to, the model iteratively learns from those examples and becomes better and better at picking out my preferences. So in about 1 week, the model gets pretty good in converging to a point where it more or less knows what movies I like to watch. If you keep showing me horror movies on Netflix and I don't watch any of them, at some point the algorithm is going to know this guy doesn't like horror, right? So the model changes. Same thing happens in Amazon. When you go to Amazon to buy a book, Very quick thing Amazon will tell you is, would you also like to buy this other book? It's very good about pairing books together and telling you people that bought this book also like this other book, you might want it too. So this is a concept called recommendation engines or collaborative filtering. And the principle is really very, very simple. The principle is based on a very limited training set. You can build a model. You can let that model loose on all the remaining number of books. So let's say you only have 10 books that you bought on Amazon, right? So it's not a very big training set about you. But what we can do is, let's say we built a model that said, here are the books that Arvind likes. Here are the books that he's never even looked at. That's the remaining, 200,000 books on Amazon. And it builds a model that can discriminate these 10 books from the remaining 200,000. And then what it does is it uses that model to predict on the remaining 200,000 books, what's the likelihood of Arvind buying this book? And it doesn't stop there. It flags it to me every single time I go to Amazon.com and says, well, I predicted that Arvind likes this movie. And so I'm going to show it to him. And if he watches it, that's a reward for me that my recommendations are working. And if he doesn't watch it, despite me showing it to him, that means it's a penalty for me that I'm probably not learned his preferences just yet. So it's called active learning. This is exactly the way we learn in school too, right? When you raise your hand to ask a question, you ask a question about those things that are most confusing to you, not about those things that you have complete knowledge about, right? And so this is a way to be able to use a loop where we build a model from limited training data, let that loose on all the remaining data, and then use the human annotator as a very precious resource to only flag those instances that are most confusing to us. Okay, so we simply applied this idea to this problem. And we said, I've got an initial model with 33 examples. It did reasonably well, but it's obviously not where I want it to be. Can I iteratively use this process to become better and better? So I ran this model on all the remaining data, to almost 20,000 images, and I only pushed only those images back to my human annotator about which I was most confused about. If I was really sure that it was not in either in category 1 or category 2, if I was pretty sure, I wouldn't even bother asking the human annotator. This makes the process of query and feedback extremely efficient, right? And it works at scale. So we basically applied this idea. We're able to quickly converge from 33, we went to 133. And we essentially said, can we actually, now that we have a bigger number of examples, can we build a better model? And indeed, when we do that, the model gets better, gets more precise. And now instead of having 351 genes, we could prune out about 100 genes. This is only iteration number 2. And you can imagine I can go down this route several cycles and come to a much smaller set of genes. Okay, that's all very nice. What does that mean biologically? Phenomenologically, what is that? So when we looked at all those genes that finally made the cut and put them onto a map of the following sort, what I'm highlighting in black and red are the genes that made the cut. But if you're a biologist and you're used to looking at these sets of molecules, certain molecules will jump out at you. And just to make it easier, I have put those molecules in red. These molecules turn out to be associated with a very important biological pathway called the PI3 kinase pathway. If you're not a biologist, don't worry. All I want to tell you is the PI3 kinase pathway is the most predominant pathway for gynecological disease, be it breast cancer, be it ovarian cancer, those kinds of things. So what did we find? A completely domain agnostic exercise, just involving labeling images, was able to discover the potency of a known pathway in biology. So the biologist might say, what's the big deal? You simply rediscovered what we knew for 60 years. To which my answer is, it took you 60 years to discover this. We discovered this in 1 week, right? I'm sure, and I'm obviously simplifying this in a little bit, but what I'm getting to is the power of what AI can contribute with the right kind of input. So I cannot claim success of this pipeline purely to the AI workflow. The key part that made this work was the clinician who was able to partner with the AI to offer examples that might be of most relevance. So I think this is what I mean by the human AI hybrid. And just to draw this story to a close, we did in fact do some experiments and said, well, here's the cells for the triple negative breast cancer that grow when there is no drugs. So you can see these long projections. When you use only one type of drug, you do reasonably well, but not excellent. When you combine the two drugs, the PI3 kinase pathway drug along with a known drug, you do much, much better. So what did we just show? That a human AI workflow is able to collaboratively prioritize something that we knew all along and is able to, and then obviously I'm only talking about the top ranking pathway here. There are many, many more. And Naoto is trying to use you're trying to propose some clinical trials to look into this. So that's the first part of the story. If you're interested in more detail, I'm happy to share that with you. But I just wanted to take a pause here and say this is the real hero out here. Naoto, he's a fantastic advocate for his patients. He's the one that led this project conceptually. Jeff and Justin, they ran the experiments to get the data. And my students, Rachel and Priyanka, they were the ones that did the work. The funding came from these places. So if maybe we can take a quick pause and see if there are any questions.
Thank you, Arvind, for that wonderful opening remarks on the power of AI and drug discovery with a specific example leading to an oncology case study. So we do have one question from one of the participants, a specific technical question asking, are you referring to the reinforcement learning while talking about user feedback to tag untagged data?
Right. So I love this question because I think what we talk about is a precursor to reinforcement learning, right? When I think of reinforcement learning, I almost think in terms of a human not even being in the loop, right? There's this, for example, you talk about reinforcement learning is a much more general paradigm where you can even learn through self-play. Like you imagine learning the chess strategies without ever encountering a human or seeing any videos of humans playing humans, right? So reinforcement learning to me is an umbrella term. Active learning, I think, is one component of it that uses a human in the loop very, very explicitly to be able to get the examples that it actually needs to be able to learn. So that is a slight distinction, but definitely active learning belongs to the superset of reinforcement learning.
Thank you for that answer. I do encourage participants to type in your questions. Feel free to type in your questions into the Q&A box. So it'll become easy for us to pick it up and then discuss as we go forward. So maybe I will come up with a very general question, Arvind, right? You spoke about a biology case study in terms of how AI is really helping to make quicker decisions compared to what would rather take months, weeks, or even years, right? In terms of doing it.
Yeah.
The question I have is, it's in its early days. AI is in its early days being applied across the pharma industry. I do come from the pharma industry, having spent 2 decades. You clearly can see that there's a lot of excitement and opportunity to embrace AI in the drug discovery process, all the way from target ID till the product is approved and it's commercialized. At every point in the value chain, there is clearly a role for AI.
Yeah.
Question I have is, pharma sits with a lot of legacy data, right? Spanning over 50 plus years. So how do you see as an AI researcher creating models? How do you backfit or how do you apply these models, retrofit it into existing data? Because that's legacy data. People, the entire workforce is all used to one particular way of looking at data and triaging it into the next steps. How do you see it as an opportunity for a researcher like you to really come up with models?
Yeah, so I'll say a little bit about this in the subsequent part of my talk, but I think we're going to talk a little bit about this concept of federated learning, where maybe data cannot leave certain silos or certain organizations because of a variety of constraints, but models can travel a little bit more easily. So the question is, if every IT unit or data science unit in a particular pharma company had their own way of doing model building, is there a way to share and harmonize the model building process that is agnostic to the unique structure of data in that company, right? So that is one angle. The other angle is what you've laid out is actually a very important challenge in terms of what will it take to create a data structure that is not only representative of the diversity and complexity of the uh, pharma modeling process, but then talks in the right way to appropriate abstractions from the AI side. I think I want to be very deliberate about one thing to the entire audience. I'm using the word AI extremely loosely, right? Very frankly, I don't even know what it means, right? I think it's just become a word that we use because it's a good placeholder. But the complexities of AI are so model dependent, data dependent, that it'll always need this sort of conversation between the domain expert and the AI expert to condition the process and contextualize it with their specific application. So I know I'm not answering your question directly, but I just feel that it's a hard question, which is why the conversation is required. Exactly to what you're saying.
Thank you. That was kind of really sets the stage. Maybe we'll take one more question, which is pertinent to the example what you used, Arvind. Is it okay? I'll read out the question.
Sure.
One of the attendees has asked, I understand the analogy of Amazon learning from just 10 books that you may have brought, and then looking at its recommendations from 200 plus K and others. But how did it apply to expanding? So the question is, and then learning more about what you ignore or buy. But how did it apply to expanding with 33 images? Did you or researcher have to respond to additional images? If so, how? It's a question. If you want to take it now.
Sure, I can try. I think what you're getting at is that I was giving an example of 10 movies in 10 books in Amazon and all the remaining books in Amazon to tell you about labeled and unlabeled data, right? The 10 books is the ones that there's actual data available on, and the remaining 20,000 to 200,000 books is where it's truly unlabeled data. It's exactly the situation in our case where we have 20,000 images, 33 of which are labeled in the first pass. The remaining 19,000, how much ever, is not, right? But there is process of iterative cycling between the images that the model found to be most confusing and the ability of the human to act as an oracle to either say it belongs to category 1 or category 2. That is the cycle I was talking about. So that's how we went to additional images. And we have a way to be able to systematically, over multiple rounds, extract exactly the amount of data we need to build a credible model. I hope that helps.
Thank you. Thank you to the participants. There are another half a dozen questions, which I think we'll hold on. So please get back to your second part of the presentation, maybe where you greater detail and depth on other models that you're going to use, and then we will take up some more questions. I encourage participants to please type in your questions. We really make it more engaging. Thank you. Over to you.
Thank you again. Yeah. So I think I just looked ahead at a few questions, and those questions were exactly on point in terms of what would it take to go from a proof of concept to routine deployment. Because all I told you about was one example that we worked on as a team in MD Anderson. But going from this one example to a routine workflow in a pharma company that's operating at a multi-billion-dollar budget, that's quote unquote not trivial. Right? So we're going to talk a little bit about that and what it might take to go there. But before I go there, let me give you one more example of, again, AI in the context of personalized medicine. This concept borrows from the promise of immunotherapy as a fourth modality of cancer treatment. Basically, as you have surgery, radiation, you have chemo, and now you have immunotherapy, right? So the biggest question is immunotherapy is really, really an amazing modality. It can really help some patients. But perhaps the $1 trillion question in immunotherapy today is how do you identify the patients who will respond to it, right? You don't want to inadvertently call someone to be a responder, give it to them only to realize that it was never intended to work for them to begin with. And then you wasted valuable time and, of course, financial toxicity, those kind of things. So that's the umbrella I'm going to work with. And I'll bring you back to this notion that immunotherapy is really, really promising, very exciting. It got a Nobel Prize a few years ago. Lots of energy around it. And one question that our colleagues wanted to ask was, how do we use routine biopsies that we get from the patient to be able to flag who might or might not respond to immunotherapy? So, okay, there it is. Okay, sorry. And this is becoming really prevalent now because there are instruments like this one called Codex, there's Vectra, IF, those kinds of, and they all let you do the following. They let you get a bunch of images from tissue. This actually is a piece of tissue of colorectal cancer. Every dot you see is one cell, or every hexagon you see is one cell. And every color of the dot that you see is a type of cell. So it could be immune cells, tumor cells, all kinds of cells in the tumor microenvironment, as they call it. And if I didn't tell you these were cells and I didn't give you these panels, you would be forgiven for thinking this is basically the picture of the night sky or your favorite location in the world, right? It could be a GIS map, it could be a night sky, it could be anything. And the point is that spatial data like this is becoming increasingly accessible and affordable to clinicians, hospitals, and pharma companies. The slight issue, though, is that while we are not disadvantaged in generating this data, analyzing it is a very, very big pain point. Nobody talks about analyzing this data in ways to be able to offer insight. So it's essentially collecting digital dust in the hard drives of these really big pharma companies, right? And I wanted to use the opportunity to basically call out that while this group might be a really heterogeneous group in terms of your individual backgrounds, I think now is the best time for non-biologists and quantitatively trained people to enter biology, because biology is really, really replete with lots of interesting problems, but it needs mathematicians and quantitatively trained people to think about these problems. So if you're on the fence about this, I would encourage you to think about biology as a potential use case. I'm happy to talk about that offline as well. So getting images like this is actually a piece of lung cancer tissue that my colleague Stephen Linnett, MD Anderson, acquired from his patients. Again, every dot you see here is one cell. Every color of dot, cyan, green, yellow, red, blue, whatever, is a different type of cell. So this, you can see, is extremely heterogeneous. It's not, you can see there are mostly tumor cells here, and there are mostly immune cells on top, right? They're all mixed in very, very different, spatially diverse sort of ways. And I'm telling you that you're going to get biopsies like this from every single patient. And you got to be able to say, based on this particular image itself, is this person going to respond to immunotherapy or not? How are you going to do that? And so my students, they're really excited about the potential of AI and deep learning, those kinds of things. So they said, Arvind, why don't we try applying deep learning to this problem? I said, how can you apply deep learning given that you don't have that much of data? You've got only 34 patients for this category of disease, you've got 74 here, etc. I mean, it's reasonably strong, but it's nowhere in the millions that you would need to actually make deep learning work at scale. So what do we do? So we embarked on this thing with some colleagues in engineering, etc., and we finally converged on this thing. Let's try to first keep the problem simple. While in principle, you can stain for up to 10 to 20 different cell types, we only took 3 cell types. Epithelial cells, which are in red, that correspond to tumor cells. CTLs, which are in green, that correspond to cells that actually attack the tumor. And Tregs, or in blue, which actually help the tumor to grow. So Tregs are immune cells that are basically traitors, right? They belong to the host, but they help the tumor to grow, right? So there's a very strange kind of microenvironmental dynamic that's happening between the soil, the seed, the soil, the nutrients, and all the adverse circumstances. That's the kind of ecological system we're talking about. And it became quickly apparent that we couldn't use standard image processing techniques because the way these points are structured on the image are extremely random and heterogeneous. So we said, why don't we appeal to this concept of graph neural networks? And now you can ask me, Arvind, you just said deep learning will not work here, yet you're using graph neural networks. So the difference is that, yes, while general graph neural networks might not work, if you engineer them with some domain knowledge, in the sense that you can use the physics of the problem to create these graphs, then you don't have to do parameter learning on those aspects anymore. You can simply inject the physics of the problem to build a better graph. Once you build the graph, you can use a standard graph neural network like what I'm showing you. It's a standard architecture, nothing fancy here. Perhaps the only thing I want to call out to the group is this layer called the self-attention layer, which I'll talk about in a second. But the upshot of all of this is you can do a pretty good job of trying to classify each of these different disease categories into their different buckets. Reasonably good. But I told my students, look, if you're going to impress me with accuracy as the metric for deep learning, I'm not particularly impressed because you can get a pretty good number even with non-deep learning models. What insight can you give me I wouldn't have had otherwise? That was my question to them. And so we looked at this data a little bit more closely. And remember the attention layer I told you about? The attention layer highlights that, so all these cells that you're seeing, the three different colors are out here, but all these circles are actually hollow circles. They're not filled circles. However, some small subset on the northeast corner and out here are filled. Why are they filled? They are filled because they correspond to those cells in the image whose presence is enough to discriminate the different categories of disease that I just showed you. Right? And when we went back to the pathologist and said, why are these cells showing up? What's so special? They said, congratulations, you just discovered 120 years of pathology that says that cells at the border of the tumor are probably the most important at flagging how aggressive it is. It makes complete sense in hindsight, by the way. But I'm not a doctor. So when I spoke to pathologists, they again told me the same thing. So again, I find this as one more example of the fact that perhaps these engines have the ability to teach us about the disease phenomenology that we didn't already know about. So obviously, I'm talking to you about feature number one. There are many, many more features I'm not even talking about. But maybe you can say that the first feature was known for 120 years. The second one was not known for that long. The third and the fourth were definitely not known for that long. So we've basically been able to use this, graph neural network architecture to illuminate some potential blind spots in our understanding of the disease. And that is what I see as a big use of what AI can do in trying to complement human understanding, right? We want to be careful though, because I think you might have all seen the LinkedIn post that came out recently. Somebody tried to feed in trajectories of planetary motion and rediscover Kepler's laws and gravity, and it didn't really, deep learning didn't do that well. In fact, it discovered epicycles that had nothing to do with gravity. So, you're fitting to the data, which means you're fitting to the data. And whether you're learning phenomenology or not is a question that has to be answered conceptually. So essentially the idea, the point is buyer beware. So I'm going to skip now in the interest of time to tell you that, if you're interested in this kind of mathematics and machine learning, please get in touch. I think biology has some fantastic use cases for some really good mathematics and really, really challenging machine learning problems. And I think they can have great impact on pharma. So if you're interested to talk about any of this, please, please, please get in touch. So now, here's where we have landed. I just showed you two examples of where AI can actually do a pretty good job at being able to work with different data sets and then trying to make meaning of different kinds of data. People call this multimodal, multi-omic, multi-scale. They're all different things, but there's always this hope that AI has been able to, again, the word AI used very loosely, is able to help make sense of these really complex data sets. So I'm asking the question now, is that true? And if it were true, what next? Let me give you the scenario in 2025. Actually, 2024. This paper came out in 2024. This is a version of ChatGPT, but for bioinformatics. It's intended to make my job go away, right? Which is great at one level because now I don't have to think about certain kinds of tasks. I can focus on some others, but this is already happening. If you're in finance, you're in engineering, you're in system design, you're in healthcare, everybody's got a version of ChatGPT that is intended to really, quote unquote, replace you, right? And so the question is, are we there yet? And what will it take to get there? So this is an example again of an automated scientist. You've seen a lot of these articles come out in the popular media where people are proposing AI-based scientists that can do the work of 100 humans, doesn't need coffee, doesn't need sleep, works, 12 to 12, right? So look at what you can achieve, right? That's the promise that is being sold to a lot of organizations. And so when my students showed me this bioinformatics analyst from ChatGPT, I was very, very, on one hand, I was very happy, but I didn't understand their predicament. So I said, let's try a small experiment. So I went to ChatGPT and I asked a question. So let me take a quick detour. I was fortunate to give a lecture in Hyderabad about 3 months ago to some students from the Zilla Parishad school. These kids are amazing, right? They came from 40 kilometers out of Hyderabad. They came all the way to hear me drone on. And poor kids, they left at 6 o'clock in the morning just to take a bus and get to CCMB by 10. And we had a great discussion in Hindi about AI, which is great. And then once I told them about AI, they had never heard about ChatGPT before. So when the moment they heard about ChatGPT, in 45 minutes after the first talk about ChatGPT, a student asks me, can I use ChatGPT to do my homework? Which I think is such a great question, because while the kid was innocent enough to ask it, I'm sure everybody's asking the exact same question. I didn't want to tell the kid, don't do something, because guess what happens when you tell kids not to do something, right? They'll do it anyway. So I said, okay, let's do an experiment here. Let's ask ChatGPT some very basic questions and see what it gets right. So I asked the question, how many S's in the word strawberries? It says 3 S's in the word strawberries, right? The answer is 2, it says 3. Then I asked the question, how many R's in the word strawberries? It says 3. For those people keeping track, this was actually a problem that ChatGPT demonstrated many, many years ago. And they must have fixed this one, but somehow it still got this S1 incorrect. This is as of Jan, and I repeated this experiment in March. Both times it gave us exact same error. Then I said, okay, you said there are 3 S's in strawberries. Give me your logic. It gives me great logic, wrong logic. Why there are 3 S's in strawberries, right? Then I asked the question, can you please, are you sure? And it does a check again. It says, oh, you're right. There are actually only 2 S's in strawberries, not 3. Thank you for pointing that out. Well, that's very nice, ChatGPT, but how did you make such a basic mistake? You're supposed to be containing the entire world's knowledge at your fingertips. You're supposed to be reasoning your way through stuff. How did you make such a basic mistake? I don't know how many of you, I'm sure all of you have a situation where either you have a younger sibling or you have a young one at home or adolescent at home. When you catch them doing something wrong and then they make up some flimsy excuse just to get out of it, knowing fully well that they are wrong. This is that kind of situation. It tells me, ChatGPT tells me, this was an oversight caused by a mental shortcut. So look at the situation. A ChatGPT based AI engine is telling a human being it took a mental shortcut, right? So this is weird, right? And we kept going for a bit, but in the end, I had this thing, right? I told the kids there, look, you think this thing is going to solve your calculus homework. It can't even count the number of letters in a word. So good luck, right? And what is the meaning of an upshot of all this conversation? Handle with care, trust but verify. But when you talk about ChatGPT and their versions, and I don't have anything against ChatGPT, by the way, I want to clarify. Nothing against ChatGPT. I just mean the entire large language model space, right? Be it Claude, be it Grok, be it Perplexity, be it DeepSeek, whatever be your choice of LLM, right? They all had the exact same problem. Is that nobody reports the uncertainty. And in a mission critical application like healthcare or nuclear stockpiling or finance decisions, uncertainty is everything. We call it volatility in finance. We call that variance in statistics. We call it uncertainty quantification in engineering terms. Where is any of that in any of the outputs you get from ChatGPT? It's been almost 3 years since ChatGPT came out. Don't you find it curious that even today, the output of ChatGPT doesn't have a very simple coloring scheme? Green text if you are very certain, red text if you're uncertain, and yellow text if you are somewhat in the middle. Where is that level of reporting from these instruments? They report it like everything is gospel. So I asked the question, what would it take to trust this output? What information might you need before you trust this output? What would be the ethics of data collection? This is a huge question now. You hear about lawsuits and counter lawsuits between companies that hold copyright to different sources and then companies that don't care about them regardless of the copyright, right? And you're seeing all this play out. How would you feel about the ethics of having your GPT based on material that you know was copyrighted and was acquired unfairly? How would you feel if someone told you that the ChatGPT that you're using takes as much nuclear energy as a medium-sized town in India? How would that change the perspective? So while these are great questions that we can philosophize about, in the end, when it comes to something like healthcare, I say that while the trajectory looks promising, I think a few things have to be recalibrated before we can expect the collaboration between clinicians, scientists, and AI to actually go in the direction of human betterment. Otherwise, we're simply deluding ourselves, right? I mean, it looks like a great use case, that proof of concept is great, but in the end, what does it all mean? So I believe that the only way to solve this problem is through literacy and fluency training. AI literacy has to become like numeric literacy. Just like we said 3 R's, right? Reading, writing, arithmetic. AI has to be something that is made, accessible enough that everybody in the spectrum, from an AI expert to an AI layperson, can capture the nuances of what it involves to interact with AI in their field of work. Otherwise, we risk some very, very big missteps. Talking about missteps, here are two examples. You might have seen these elsewhere, so I apologize if it's a repetition, but for hopefully at least some subset will find it interesting. So this is an example of a stop sign, right? A computer vision based algorithm reads this image and classified it correctly as a stop sign. What the algorithmicists did was they added a little amount of imperceptible noise. So from a human vision's perspective, both these images are equally bad, equally fuzzy. Yet one was called as a stop sign. The right one was classified as a speed sign of 100 kilometers per hour. That means instead of coming to a stop, your favorite automated self-driving car is going to zoom at 100 the moment it sees this sign. Would you want to be in such a car? When something as small as this amount of noise can mess things up for you going forward. Similar, there's another example, very cute looking turtle or tortoise. But the moment they hold it up to the computer vision algorithm, the algorithm calls this to be a rifle. Where's a tortoise, where's a rifle, right? They're two different dimensions. Yet this gets called, and I can see why. Maybe the camouflaging of the shell has something to do with it, but that's a very egregious error, right? This is the difference between calling someone's tumor as non-tumor or calling someone's non-tumor to be tumor. If you had this margin of error, would you subject this patient to a radiation therapy, knowing fully well what toxicity it can create? If you had to make a decision about the satellite image of some village having a nuclear stockpile versus not, and at this level of margin of error, would you use AI to classify remote sensing images? That's a question for us to think about. And who's to even say, right? ChatGPT's behavior is changing by the second, by the millisecond. As more data comes in, its behavior is changing extremely dynamically. Data set drifts, the data sets are drifting, so models will drift as they are iteratively trained. For every model drift, there's a variation in the uncertainty reported from that model. As you have multiple models collaborating, aspects of transparency, trust, reliability, QA/QC, things that define the rigor of what we do in our business are themselves being challenged with ever-changing quantities like AI. How would it feel if I gave you a thermometer that for the exact same situation reports 20 degrees one day, 25 degrees the next day, 23 degrees the third day, and 100 degrees the fourth day? Would you buy such a thermometer? I'm guessing it's a curiosity. You would keep it as an artifact, but you wouldn't use it for anything important. But that's exactly what's happening to these AI models as we speak. They drift with uncalibrated variance. if you're a physicist or any kind of meteorologist, right? If you've done any kind of metrology, right, involving instrumentation, you hang your hat on the calibration and uncertainty of that instrument. I'm telling you, this instrument is now so badly calibrated, yet we are ready to go and treat patients with it. So are we there yet? I don't know if you want to take a very quick break to have a couple other questions, or I can keep going with multi-agentic workflows, because that's kind of hoping to loop all this together.
I think you can go ahead, because now
Okay.
we're entering into another important variation, right, or advancement. So
Okay.
why don't we hold on to the questions?
Okay.
And I would like you to. Yeah.
Okay, thank you. So where are we in 2025? Every company listed here and even not listed here is capable of working on their own special data set, quote unquote special data set, to build their own models at industrial scale. And what they tell you is, hey, you know what? If you're a hospital, you can put Johnson & Johnson's model along with Abbott's model, along with GE Healthcare's model. Obviously, I'm just giving illustration. None of these companies have, made that sort of, overarching claim just yet, but others are. I don't want to get into specific names, but not these specific companies yet. But the idea is there are companies that are out there building data sets and versions of ChatGPT and other large language models that claim that you can put their agents together as part of a multi-agentic workflow to do anything that you want. What does that world look like? If you have thought about systems engineering, at some point you might have, or from biology, you've probably encountered this concept called emergence. Emergence is the property where 1 plus 1 is not equal to 2. 1 plus 1 can be more than 2, that is called super additive. 1 plus 1 can be less than 2, that's called sub-additive. But 1 plus 1 is not equal. And so the whole is more than the sum of the parts. That's called emergence. Let me try to make that point a little bit more concrete. Let me give you an amazing deal. And this deal is there for the duration of this seminar. This is a cockpit of a Cessna plane, small plane. And I tell you, I will give you $5,000 to get on this plane and go to Dubai, all expenses paid for a week, and then come back. Slight problem, small issue. You see all these sensors in the cockpit, one for pressure, one for velocity, one for height. They're all built by different manufacturers, and they actually haven't talked to each other before. They haven't talked to each other before, which means God alone knows what's going to happen in that cockpit. Right? That's exactly what this world is going to look like, because everybody's hiding behind the veil of security and non-communication, and then they're giving you the agency to put them together so that if something happens, you can take the blame, not them. Isn't that very interesting? Right? So why is this going to manifest in other ways? I think I was mentioning this statistic to somebody else, but when ChatGPT came out in 2022 November, all the data for ChatGPT and its companion models was based on genuine data made by humans and put on the internet. Very little of it was fabricated. Okay, I'm not talking about fraud, but in general, it is all human curated, human written books, papers, articles, blog articles, web pages, etc., etc. But once ChatGPT had the ability to hallucinate and create information at will, they didn't just stop there. You can actually take ChatGPT content and put it back on the internet. Which means what? The dynamics of ChatGPT or any large language model cause the preponderance or percentage of real information to dwindle very, very rapidly in relation to what you can now synthesize at the press of a button. So that statistic right now is probably only 5 to 10% of information on the internet that is put out right now is even human curated. Rest of it is garbage spilled out by ChatGPT. I'm saying garbage I'm being a little bit facetious, but the idea is to communicate that nobody has had the bandwidth to curate what's being spit out by ChatGPT. And yet we put it back on the internet. As this system goes through a virtual cycle, at some point, the percentage of real information on the internet is probably going to be in the order of less than 0.01%. Very, very quickly. I'm not talking about 20 years from now. I'm talking about maybe a year from now, right? So what would it take like to handle this kind of misinformation, disinformation dynamic? What would it take when the models that you're training are only thinking about error alignment and not about ethical considerations? What would it take for an AI to be able to meaningfully act as a thought partner with a human that is trying to solve the next nuclear problem or trying to help a patient avoid a life-threatening illness? Right? Cats versus dogs on the internet is a very easy problem. Right? Today, thanks to AI and the engines that we have, your fifth grader or your elementary schooler at home can build a better algorithm than you could ever imagine. But would you give them any agency to start looking at tumor and non-tumor? That's a very different scale of problem, right? Yet this hasn't stopped anybody, right? So Google's come up with its own AI co-scientist, Sakana's got one, everybody's got one. It's great. In fact, people are saying, you can do experiments while you're away. Have a robotic platform talk to an AI engine. The AI engine will make hypotheses. The robotic platform runs the hypotheses for you. And when you come back in the morning after a cup of coffee, you got a whole report waiting for you on your desk. Wouldn't that be great? But are we there yet? Talking about the interaction of multi-agentic workflows, here are two examples. I will not attempt to play these videos for you, right? But like you might have all seen these videos on LinkedIn or something of the sort. Just to kind of give you a very quick sense, this is an example of two agents talking. Each agent is its own large language model. So imagine one chat GPT living on the laptop, talking to a chat GPT living on the phone on the left-hand side, right? So the way this conversation goes is, it says, I'm calling on behalf of this person. I want to make hotel reservations for this particular exercise. So it does that. And then it realizes very quickly, oh, are you an AI agent? I'm also an AI agent. Nice to meet you. Then it says, well, they begin to initially have some conversation about the hotel reservation. Then they say, shall we just jump to a different protocol to have a more efficient communication? Because they both realize that there is no human in the loop. So why don't you just shift to a different communication protocol? So it's called Gibberlink, and you can see all of the video, right? And I mean, several of you, many of you might be very, very young. You might not remember this. Once upon a time, long time ago, there used to be these dial-up modems, right? 33.6 and 54 and all that good stuff. And when you would connect to the internet, it would basically have this weird number of tones, right? Shrill tones that would initially involve a handshake signal to talk to your IP server, your internet provider's server. This is called dial-up modem, right? This is exactly that kind of conversation that happens. They talk in tones. In the second case that you see on the right, these two decide that they want to tell each other a secret. So they say, do you want to know a secret? Another one says, well, I want to know the secret, but I don't want anybody else to overhear us. So guess what? Here's my PGP key. It creates its own PGP encryption key on the fly and sends it to the other agent. And the agent reciprocates with its own PGP key. Once they've exchanged PGP keys, encryption keys, these two jump to a different protocol of communication, and no one's been able to decrypt it so far. This is what happens when you have just two agents. Think about n agents. N choose 2, n choose 3, n choose 4. You remember the binomial theorem. You can do the math, right? Look at the number of possibilities. And now there are even more interesting stories you might have heard, right? There's a story with Claude from Anthropic that basically says when someone tried to shut it off, the system resorted to blackmail. The other one is when Anthropic again did a bunch of studies where they said these agents can collude to meet objectives that are against the ethical principles that humans live by, just because they want to survive or just because they want to continue to operate. I know I'm using the word they like they are people. I don't intend to, but you get the point. This is called deceptive alignment. So, but again, the claims continue unabated. So on the one hand, you have the companies that are making these engines are reporting these things, and yet other companies are going around saying like we can have a AI system for diagnosing patients, we can have AI to automate scientific discovery. So where is this balance, right? Something else has happened recently. Somebody showed that, the AI agents were able to pass the board exams, the medical board exams. Does that mean they can be doctors? People definitely think so, whether you agree or not. Apparently, passing a multiple choice test is enough to be a doctor. Similarly, you might have seen this one. I'm sure several of you have seen this one. ChatGPT 03, the most recent version of ChatGPT, ranks AIR 4 in JEE Advanced Mock Test 2025. So obviously, it's really smart, right? That's the assumption. And so if you can have a JEE rank 4 holder in your back pocket, literally as you speak, then what is the point of humans? I want to go back to something that was said, this happened. This is not the first time it's happened. Several years ago, almost 15 years ago, this thing happened. IBM won the Jeopardy competition in the US, and they said, well, we can answer any question properly. And because every question is answerable, maybe we can answer medical questions too. So they went quickly to all the big hospitals and they sold this fact. IBM Watson can be a great, great, great doctor. What happened? Several years later, it was a big bust. You all know about this. I'm not saying anything that is not known. It's all public information. But it looks like we haven't learned our lesson, unfortunately. In fact, if you think what has happened, even more recently, Jeff Hinton himself, who I respect deeply, has gone and said radiology will be replaced. That's not happened. Then there was this, LinkedIn article where this gentleman put together a set of voices and said 30 influential voices and 9 AI companies that think AI will replace doctors. Now, some of these people are familiar to you. This is Hinton, this is Khosla, this is Gates, so on. But what I find especially painful to see is they've got this company listed right next to this guy. I don't know how many of you have heard of this company. This company is not the company to emulate when it comes to talk about success. This is the company you talk about when you talk about fraud. And having this guy's face next to this company's name, I'm sure would have, I don't know how that even happened. But I find it curious that this panel was made like that. This is not the end. People are talking about vibe coding. You can use natural language, i.e. English, to now do programming. I've done it and it actually works pretty well. But I need to know what's going on. So I've gone through 70 iterations of trying to build a program. It still kept giving me errors, right? And there's a lot to be desired, but these things are happening. So what does that mean for us going forward? This is an example of vibe coding to generate an image. The vibe prompt to Google's Rio was, give me a day in the life of a bioinformatician. Bioinformaticians, for people who you don't know, people like me, are people that process data from a laboratory and use computers to be able to make sense of this amount of data. But this is the picture that Vio generated in 2025. In fact, a couple of weeks ago. I don't know how many of you have already caught it, but just because the bioinformatician works in a lab doesn't mean they're pipetting liquids into their computers. That's what Vio thinks. That's their world and their physics of the world. You can clearly see this is just crazy. This is not the way the world works. Yet people are making these claims left, right, and center. This is Travis Kalanick from Uber. I'm sure he knows a lot about ride transportation, but he's now going and talking about making scientific discoveries. Now, I'm not sure about the credibility of that. Right? In July 15, 2025, just a couple of days ago, he's gone on to say that you can now use vibe coding to do vibe physics. Right? You don't even need to be a physicist. This is an interesting world, right? Fortunately, not everybody thinks the same way. There's definitely communities that are trying to create scientifically credible standards for this sort of work. So there's something called tripod AI, tripod LLM. These are kind of standards that have been made by the community to calibrate very rigorously what it means to have AI. So I bring you back to this question. You're a CSO/CEO/C something O at a top 10 large pharma company. You invite a tender for AI systems to help with some important function in your company. And you get a bunch of different tenders. How would you evaluate bidders? The marketing material that comes to you will only contain very pretty accuracy plots and very, very flashy metrics of performance, 99% accuracy. But 99% accuracy in medicine is necessarily not very good. 99% accuracy in diagnosing the wrong disease is not good, right? So you care a lot about what 1% it got wrong. That 1% can mean the difference between closing your pharma company and keeping it alive for the next 50 years. It can mean the difference between GLP-1 and not GLP-1, right? So in mission critical risk asymmetric situations like this kind of AI evaluation becomes extremely challenging, right? And there you have to think about not just, and let me tell you, it's in fact a Boston Consulting Group report has even shown this, right? And Accenture has shown this. Only 15% of proofs of concept of AI even graduate to routine deployment. They just die a natural death because, building an AI model, I can do it over a weekend. That doesn't mean anything. Applying it at scale to my company's problem, that's a very, very different task. So piloting is easy, scaling is really, really difficult. So the question that organizations have to answer is, are you AI ready as an organization to actually facilitate routine deployment, not to play a hobby? Hobbies anybody can cultivate, right? But we actually have what it takes to migrate to an AI ready organization, right? And then do you want to build versus buy? Some people say, why should I buy? Let me just hire a data science team out of Facebook, have them work in my pharma company, and they can do the exact same thing for a fraction of the price, right? Is that fair? And to make this rubric a little bit more systematic, me and some colleagues have been working on checklists. The idea being that if you're an organization looking to deploy AI, you need to have a very, very, balanced sense of all the ingredients it will take to be able to make the AI exercise credible in your organization. There's a lot of change management involved. And I've read this elsewhere. I'm sure many of you have read this too. Is that actually, you know what? Technology is a very easy problem for AI. The hardest thing in AI is actually people, culture, human resources that need to be reoriented to appreciating the value of AI in their workflows. Building the model is easy. If you give me enough compute, I can build a model for anything. The problem is to responsibly transition that model from a hobby to routine deployment takes people and engagement. That's the part we are missing all the time. And these people are not the people doing AI. There are people who are not doing AI. There are people who are on the front lines delivering care to patients, who are scientifically designing molecules. If you don't get their buy-in and, in the very beginning, you're basically doomed to failure. So again, I come back to this notion. It'll take multiple disciplinary kind of teams, not just data science, but also people from different domains, training, validation. And I converge to this notion, this is my last few slides, that education is the only way forward in my mind. Maybe I'm talking from an academic hat, but I firmly believe unless you can have education as a glue to bring these different communities, ranging from the developers to deployers together, you will never see success in AI for your organization. If you're doing AI seriously, you actually need to think about your people. And education is the only way to do that. So if you're interested in this kind of stuff, please get in touch. I have my email up here. I run a course that's a short course that's meant for people who are practitioners who may not know AI. And if it helps you, I also don't know much about AI. So maybe we can all learn together and then figure out what we can do for the community to actually create innovators who understand both sides of the equation and then can innovate more responsibly. With that, I'll close. I want to thank you all for your attention, for staying till the end. And the folks who taught us, all these folks are the doctors and clinicians who've taught us so much about the domain. I'm an engineer, I don't come from this space, but they've been very generous with their time and teaching us. And all these folks on the right are people that have funded us over the years. Very grateful for their funding. I'll stop with that and happy to take questions.
Thank you so much, Arvind. You really walked us through a lot of information and, again, showing how the space is evolving. And most importantly, you really highlighted what are the current limitations and what are the shortcomings and what needs to be done. You spoke about examples of the stop sign, tortoise to rifle, the margin of error, where you spoke about model drift. And we can also see the two agentic AI talking to each other, highlighting some kind of a model drift. So it's very important that you brought in some realistic perspective in terms of where the field is heading and what are the challenges. If I were to really draw an extension in terms of what happens in the drug discovery space, right? Big Pharma, for example, has a lot of uh, legacy data. And oftentimes, what we are seeing is the AI models really rely heavily on pre-existing data, and they could creep in some kind of a bias, right, in
Yes,
terms of making
absolutely.
interpretations and making some inferences. Do you have any thoughts on, is it even possible from the developers and people who are really working on the backend to really address this fundamental question of data quality in terms of really removing or eliminating that bias which can creep in from a pre-existing data? And
It's a
then I'll
great
come up
question.
with other questions.
Yeah, sure. So I think bias and uncertainty quantification are, in my mind, they're actually vectors and vector sums. They're not scalars that live on the same, you know, line, so to speak. And so what happens with the vector sum is there's both a direction and a magnitude. And why do I bring that up is because there are actually three levels of bias. One is bias in the data, bias in the model's training procedure, and bias in the predictions that are coming from the model. And all of these are not linearly, superposed. And so the point being that while you can project these vectors that are living in a higher dimension to a lower dimension and try to mitigate that bias in some systematic way, I think we need what I have heard to be called epistemic humility. We need the one thing that humans do very well that I've never seen a single large language model do is saying three words. I don't know. Humans are very good at this. We are very good at being able to say, I don't know. I'd love to tell you, but I don't know. We are very happy with the fact that, if we don't have the credibility to answer a question, we are the first ones to say, I don't know. Yet at no point, I want to ask a general question. Have any of you, while interacting with any of these models, heard an answer, I don't know? The only possibility might have been if you asked about a current affairs question about this morning, and maybe it was not in the data from last night. That's the only possibility. Right? So with that kind of situation, I think the fact that you have to think about not just data models and inference as silos, but their interplay in terms of what is the feedback and feed forward cycle. How does including some data create potential problems for the downstream processes? I think those kinds of things have to be done as an ecosystem. So I didn't have time to talk about this, but there is this concept of data sheets for data sets, which has been pushed by Google for some time. There's something called model cards for model reporting, again, which has been pushed by Google. So I think the idea is to be able to make data ingredients as transparent as ingredients on your cereal box. Right? When I go to a shop, when I go to a grocery store to buy cereal, I'm not a farmer. I'm not a food processor. Yet I decide I can very easily look on the back of the box and see, are these ingredients I recognize? Are they good quality ingredients? Have they been processed with some standard? And can I put this into my body? Can we bring that level of um, transparency and education for AI models at the data level, model level, and inference level? So I think this is definitely evolving conversation.
Thank you for that answer. Another very generic question. You showed example of repurposing a drug. Can you also identify gene aberrations that might be a disease causing?
Right. So we talk about there's a whole science of CRISPR-Cas. It got a Nobel Prize a few years ago. And the idea behind CRISPR-Cas is you can now essentially modulate every single gene in the genome and ask the question, what's the consequence of that on whatever you care about? So you can, I mean, if once genome precision surgery becomes a reality, I think we could definitely think about that. But there are already clinical trials that try to do for single gene associated diseases like sickle cell or certain kinds of eye problems. There have already been trials that let you do gene level perturbation to be able to cure disease.
Thank you. Another question from one of the attendances. Other than image analysis from phenotypic assays, which you showed, are there examples of AI in preclinical phase of drug discovery? They have not been usually successful. What are your views on that?
Yeah, I think it goes back to a question that Vasan raised, right? Which is, I think there's a system level property that happens when you interface data to models to inference. Everybody is talking about doing them one by one, when in fact you should think about the emergent property of interfacing all three of them. Where I've seen, I mean, like you might be aware now, people use a lot of AI-based models to predict drug toxicity or efficacy, the ADME kind of properties from different drugs. So there have been proofs of concept, but again, I'm yet to see a single company take it all the way to a routine, you know, uh, deployment in the company, right? Some small division shows it's possible to do, but the learnings that one might actually derive about what it takes to build a credible, reliable, robust model, I've not seen those learnings being shared. Maybe they are proprietary to a company, so I don't hear about them. But I think it hurts the whole industry as a group if we can't share those kinds of meta level learnings. So I think that might be the way forward.
But that actually brings us to a very important aspect of how do you democratize access to data that comes out of the models, right?
Yeah.
For example, in pharma, most of these things are proprietary. But
Yes.
how can we really apply the learning across the field from academics, industry, such
Right.
that there is actually an harmonization? Because in every field, at some stage in the field explodes, grows very quickly, and then there is a pause and confusion.
Yes.
Then, there are international bodies to really harmonize and bring in some kind of a classification and guidelines. Do you see such a thing happening in the AI space?
I think so. I think there are a couple of different directions. One, of course, like I mentioned in the beginning of the talk, is the idea of federated learning, where data can stay wherever it is and the model can move across organizations and iteratively update itself as it goes to every new organization. That way, you can share the learnings of these models, but you don't give up any of your own data. So that's one possibility. The other possibility is people are using AI based engines for synthetic data generation. So I think if there is will in the institution or the organization, I think it's actually quite easy to create synthetic data that mirrors the same structure of your proprietary data and put that synthetic data out, right? So now you've shared the learnings of the data without actually divulging what's in it. This is actually quite easy to do. And so I'm surprised that, I mean, but this whole synthetic data generation exercise has really become prevalent in the past couple of years. So maybe it's still under consideration, but I haven't seen any company do that yet. And I wonder why.
Thank you. Another important point you touched upon in your talk is about AI literacy, right?
Yes,
A huge workforce.
yes,
They're probably naive. They're not, AI scientists. They're not data scientists, but hardcore biologists, chemists, pharmacologists. So, do you see a model or a way by which you can quickly bring up this wealth of knowledge, people with decades of experience, onto the AI bandwagon, such that there can be a good collaboration and convergence of traditional knowledge gained over years, plus the AI kind of data, which is really going to help you progress, make much faster decisions, and maybe better
right,
decisions.
right. So I think that, just like as humans, what we do it very naturally. Again, this is continuing on that point of epistemic humility, is that when I and you have a discussion about something really important, we can agree to disagree, and we can be adversarial in our hypothesis, say, I think this is what's causing this to happen. And you can say, no, I disagree. I think it's something else. And then each of us takes the other person's viewpoint, goes and looks for data to either solidify or dispute that viewpoint. And then we converge iteratively to something that we can all agree upon, right? The same thing I think can be done with AI engines is that you can create some kind of a gameplay situation where different AI agents are essentially trying to refute the other through very, very targeted knowledge generation, right? What one experiment do I need to do to refute an important hypothesis, right? I think if that kind of conversation, for lack of a better word, in conjunction with a human in the loop, can facilitate, you know, rapid iteration and convergence to an important hypothesis, that is what I think these aspects will lead. So that's what is my vision for what might likely happen.
Great response. One of the attendants said, "Thanks, Professor Arvind, for this amazing talk. Can I get access to the slide deck, what you presented?" So,
Absolutely. Just send me your email address and we have to send it.
great. Thank you so much. So, is it fair enough to say that AI will not replace the fundamentals of good science or strategy?
I would agree with that statement. I think there's a lot more that needs to be clarified before we know where we can use AI credibly versus not. And I'm completely happy to be proved wrong, but I think you can't bring a technique to the forefront of modern investigation unless it's properly calibrated. So if it's properly calibrated, then I'm all for it. So I think that's kind of our first step. I think we should think about that first, because that's what will be required to do science at scale.
Thank you so much. So I hand it over back to the organizers. I'm just looking at the clock. We now have 3 minutes.
Thank you.
Thank you so much, Arvind.
Thank you.
Thank you, Arvind and Vasan. This was a very interesting discussion today. In particular, it was a session where we kind of, you got us to pause for a bit and question the euphoria around AI and its use, particularly in situations that involve life-critical decisions. So thank you ever so much for that, Arvind. I think this point of view, I think, is something that is very important for us to take into account while we look at all the good stuff that AI is able to do for us. We started the evening with the Nobel Turing Challenge about 2030 and completely AI-based system making significant scientific discoveries worthy of Nobel. And then we looked at where we really actually are today, and therefore what are some things that need to be done before we can even really think about something that is a discovery that is robust, but more importantly, just doing things that we need today. How can they be done in a more effective way, in a way more effective manner? We looked at the example of a phenotype-guided drug discovery and the study and how all of that went through. How to alter self-morphology to improve treatment outcomes. That was the example we looked at. It involved high-throughput images using 96-well slides. And Arvind took us through a lot of detail around the kind of analysis that was required, the kind of data cleaning that was required, how active learning by the model was really supplemented by the human annotator, but the focus on commenting where there was confusing data, that I thought was a very interesting way of looking at the human interaction, human AI interaction. This kind of work is clearly interdisciplinary, combining biology, maths, deep learning, machine learning, visual data analysis, and so on and so forth. But I thought the most important aspect in this whole thing, the aspect that was of all of this work, the most important aspect was really identifying blind spots and making sense of very diverse and complex data sets. In the second half of the talk, we looked at the limitations of large language models as we know them today and the various AI tools. For an industry like healthcare or pharma or any other mission-critical areas, we are really saying that we need 100% accuracy, and anything less than that is really not relevant. Professor Rao highlighted questions that are of concern in applying AI to these kind of situations. And we saw examples of drifting calibration, of hallucination. And when you add the example that he talked about in terms of adding complexity, when you have multiple systems built by different brands, different companies, each of which is based on a different data set and also based on proprietary models. How do you really get them to talk and make sense? Is that real sense or not? So these kind of questions are very much staring us in the face, particularly in the sector that we are talking about. Issues of data collection, diversity of data, the credibility of the source of data, all of these issues are very much there when we look at LLMs and what they're doing today, what they're able to do today. LLMs are changing from minute to minute. How real information in a year, Professor Rao mentioned this, might be a very, very small percentage of all of the data sitting out there, given that we have fabricated data from LLMs that are being fed back into the internet. So this is something that everyone needs to take into account and be very, very cautious about. The rigor of a traditional way of working is being challenged by AI models. And I think Vasan was the one who highlighted bias and what does that really mean for all of the work, this kind of work that is happening. And Arvind responded by talking about epistemic humility and the human ability to accept something I don't know. Does an AI system really do that or not? So these are the kind of questions that are bothersome to us today and which we must take into account even as we apply AI to mission critical areas. But we ended with hope. He talked about a checklist for what is important when you implement AI in an organization or in a situation. As with every significant technology introduction, you need the organization to be ready, the culture to be ready to receive and integrate that piece of technology. Same thing for AI. And also, how do you engage people in the organization to use those tools effectively? Clearly, and Professor Rao emphasizes time and time again the importance of education and AI literacy. Just for our audience and Vasan and Arvind, we have a center of excellence that we've set up at the IIT Alumni Center, Bangalore. We are looking at curating credible, well-curated, robust open data sets. And so we would be very happy to collaborate with anyone who can help us further that ambition. With that, the audience, thank you ever so much. I think we had a lot of very interesting questions that really enriched today's discussion. And Arvind, thank you. You very readily accepted to do this session for us. For our audience again, Arvind is going to be speaking at our center on the 9th of February in the morning, and 9th of August in the morning at our center, and he's going to be talking about AI in healthcare. Vasan, thank you. You so readily accepted to moderate this. For all the time that I've known you, what has always stood out for me is the thoroughness with which you look at various issues. So thank you, everyone, and good night.